Hello and welcome to this video. So in this video, I'll be talking about point-to-point protocol implementation and configuration. Point-to-point protocol is one of the several protocols that are used in a wide area network. It boasts several advantages, as we are going to see in this video. It is a common wide area network data link layer protocol, works at layer 2. And it is used for point-to-point data encapsulation and transmission on full duplex links. What this means is that point-to-point protocol is used in scenarios where the only thing connected on the other end of a device is one other device. There can't be more than one device. It's just one point to another point. It's just device to device. So anything that gets out of this router has only one destination it can go to, that router. So if that router sends it elsewhere, it's that router's problem. But as long as it gets out of this guy, there is only one guy it can reach to, and that is that guy right there. So point-to-point protocol provides two authentication mechanisms or modes, supports password authentication protocol and also challenge handshake authentication protocol. That's PAP for password authentication protocol and CHAP for challenge handshake authentication protocol. We'll talk about those in a moment. Point-to-point protocol features high extensibility. For example, we can extend this protocol by encapsulating its frames inside Ethernet, thereby having point-to-point protocol over Ethernet. We do that when we want to transmit packets or point-to-point protocol packets over Ethernet. Point-to-point protocol also provides LCP, or the link control protocol, which we use to negotiate link layer parameters. We're going to look at this process in a moment, such as the maximum receive unit and the authentication mode. Point-to-point protocol provides various NCPs, or network control protocols, such as the IPCP. This is the network control protocol that's used for negotiating IP parameters if the network layer protocol is IP, which is the case for this course, this chapter. So in our example, you have R1 connected via serial link to R2, and this is a point-to-point protocol. When you use a serial connection between any two routers, any two Huawei routers, even in ENSP, it's going to default to PPP data link protocol. So what happens when we connect two devices like this and power them up and there is power on these links? What is going to take place? Let us look at the link setup process. So the setup of a PPP link involves 3 steps. First of all is the link layer negotiation. There are several things that will negotiate. The devices need to negotiate at the link layer. This is the first step. The second step is authentication negotiation. Now, during the link layer negotiation, we also negotiate the authentication mode. Now, if the authentication mode was negotiated in step 1, it means we shall need to negotiate the authentication itself also. At this, the parameters for the authentication. But if it was not defined in step 1, then step 2 will be ignored. Step 2 is an optional step. The third one is network layer authentication. Again, in link layer authentication, we use link control protocol packets to negotiate link parameters and establish link layer connections. As I've mentioned, authentication negotiation is optional, and we use the mode that has been negotiated in the very first step, the link layer negotiation. The third step is the network layer negotiation, where we use network control protocols. In our case, we'll be speaking of IPCP, or Internet Protocol Control Protocol, NCP negotiations, which we use to select and configure network layer protocol parameters and also negotiate other network layer parameters. So 3 steps. First of all, we do link layer negotiation. Secondly, but optional, we do authentication negotiation. And thirdly, we do network layer negotiation. If authentication is not enabled, then we shall go from 1 and jump straight to 3. Once these 3 steps are done, the PPP link is up and it's ready for communication. Let us look at the states involved. Now, the link layer negotiation, which I mentioned is the first negotiation that happens, takes place in the establish state. Look at the authentication negotiation. This takes place at the authenticate state. And finally, the network layer negotiation takes place at the network state. So what exactly is taking place here? Now, a PPP link can be set up after going through link establishment, link authentication, and network layer negotiation phases. Those are the 3 phases I've talked about. Let me explain what is happening here briefly. So 2 communicating devices, for example, router 1 right here, connected to router 2 right here and using a PPP link. When these two devices enter the established phase, they start to set up a PPP connection. As long as this router is powered up and this router is powered up and the physical link goes up, they go to the established phase, up from the dead phase, and they start to make up the to set up a PPP connection. In the established phase is where they are going to perform link control protocol negotiations. They are going to control to negotiate a number of things. They are going to negotiate the maximum receivable unit. They are going to negotiate the authentication mode. They are going to negotiate the magic number. They are really going to negotiate a number of options. Now, if and only if this negotiation is successful, if the link layer negotiation is successful, we shall go into the open state. The devices get into the open state, which means that the lower link layer has been established. So in the open state, if authentication has been configured, the devices will go right. If it is configured, they will go to the authenticate state. If it is not configured, if authentication has not been configured, they will go straight to the network state. So let's say in our example, authentication has been configured, the devices go to the authentication phase. Now in the authentication phase, we do link authentication based on the authentication mode that was negotiated in the first phase. Remember, I talked about maximum receivable unit, I talked about the authentication mode also here, and I talked about the magic number. If the authentication mode was configured or was set up as either password authentication protocol or challenge handshake authentication protocol, it means that this phase, the answer to this is a yes, and this phase is going to be undergone. If authentication was not configured, the answer to this is a no, in which case we go straight to the network control protocol negotiation. So if authentication is configured, we go to the authenticate phase, and in the authenticate phase, the link authentication is performed based on the authentication mode that has been negotiated in the link establishment phase. As I've already mentioned, there are two authentication modes available in point-to-point protocol. We have password authentication protocol and we have challenge handshake authentication protocol. I'm going to talk about this in a moment. If the authentication succeeds using one of these, if the authentication succeeds, the devices will go into the network phase only if the authentication was passed. If the authentication was failed, they will go right to the terminate phase where they go back to the dead phase. So let us assume the authentication was successful, and so we went to the network phase. In the network phase, we use NCP. There are several NCPs, network control protocols. In our case, we'll use IPCP, which is used to negotiate IP parameters. We use IPCP to negotiate the PPP link and select and configure a network layer protocol and to negotiate network layer parameters. In our case, again, we shall use IPCP to negotiate IP parameters. And once this negotiation is done, of course, we shall have our communication, and after the communication is done, we shall go through closing back to the terminate phase and get right back to the dead phase. So during the PPP operation, the PPP connection can be terminated really at any time. So we are mentioning here a number of points. This point we terminate, and after the network exchange we terminate, but it can really be terminated at any point along the way. It can be terminated at any single point along the way. There could be a physical link disconnection, could be authentication failure, could be a timer expiry, could be a connection closed by administrators, several factors. The point is, if the link is terminated, we shall need to go back to the dead phase. So in the first phase I mentioned, we use the link control protocol packets to negotiate. Right here we shall use the IPCP to negotiate. Let us look a little bit at the link control protocol packet format. So this in fact is the PPP frame format. Right? It's made up of the flags field, the address field, the control field, the protocol field, and the information which we are encapsulating in our PPP header, and the frame check sequence and the flags field over the end. Please note that both there's a flags field at the end and the flags field at the very beginning, and they both have the exact same value. What's the purpose of this flags field? The flags field identifies the start and the end of a physical frame. It is really a binary sequence of 0 and 6 ones and another 0. This is what we translate to 7E in hexadecimal. The second field after the flags field is the address field. And the address field in a PPP frame, well, you would expect destination address. And yes, it is the destination address in the PPP frame, but it represents a broadcast address and it has a value of all ones, which translates to FF in hexadecimal. Now you would be wondering, well, wait a sec. I am connected to just one other device, which is the definition of point-to-point connection. Why is my destination address a broadcast address? Why does it have to be a broadcast address? Well, this is a way of PPP acknowledging that I'm just connected to one other guy, so I don't really need to know their address anyways. I can just send to everyone. Everyone in this case is still one person, so no need to worry about that. The third field is the control field. And the control field of PPP data frame is filled by the value 03 hexadecimal. You write it like that, 03, which translates to 11 in binary. So we'll have 6 zeros right here and 11. Why? Because the field is an 8-bit field, 1-byte field. After the control field is the protocol field. And the protocol field has the value C021. C021. So the protocol field indicates the type of protocol that packets that are inside this frame are in. Think of the protocol field like our type field or the protocol field of IP. It's basically saying what is inside this PPP frame. So for example, the value 0021 signifies that we are encapsulating an IP packet. Inside here in the information field is an IP packet. If the value in the protocol field is 8021, it means the information we are trying to carry around here is an IPCP packet. If the value is C021 hexadecimal, it means the information we are trying to carry right here is a link control protocol packet. If the value is C023, it means the value we are trying to carry in here is a password authentication protocol packet. And if the value is C223, it means what we are carrying inside here is a challenge handshake authentication protocol packet. So these are some of the more common values inside the protocol field. So different values represent different things. The information field is like the payload field. This is the one that specifies the content of a protocol that has been specified by the protocol field. Again, if the protocol field has 0021, it means it's an IP packet, and that packet is going to be right there in the information field. The information field specifies the contents of the protocol. The maximum length of this field is also what we recognize as the maximum receivable unit on Huawei devices, and the value default is 1500 bytes. So when the protocol field is 0xC021, it's a link control protocol packet. Now the information field structure is going to include an identifier, is going to include the length field, and it's also going to include a data field. So the identifier, the length field, and the data field are the ones going to be in the information field if it is an LCP packet. And since we are dealing with the LCP negotiation, let us look at the contents of this. The identifier field is 1 byte in size and is used to match requests and responses. The length field specifies the total number of bytes in the LCP, the entire LCP packet, and the data field is simply a sequence of TLVs, type length value parameters, for negotiating configuration options. This is where the negotiation values actually are. The maximum receivable unit, the authentication protocol, and other values like that. Common configuration parameters that are carried by the LCP packets include the maximum receivable unit, authentication protocol, and magic number. And as I've mentioned, on VRP, which is Huawei's network operating system, we use the maximum receivable unit derived from the maximum transmission unit that has been configured on the interface. The common point-to-point protocol authentication protocols, as I've mentioned, are point-to-point protocol and challenge handshake authentication protocol. It's going to be one of these. These are the most common ones to be used. So the two ends of a PPP link can actually use different authentication protocols. Both of these authentication protocols work two-way. So if I have router 1 right here connected to router 2, router 2 will authenticate router 1, but router 1 will also need to authenticate router 2. So what we are saying is that router 2 can use challenge handshake authentication protocol to authenticate router 1, while router 1 is using password authentication protocol to authenticate router 2. However, the authenticated end must be able to support the authentication protocol that is required by the authenticating end. If router 2 right here is using challenge handshake authentication protocol, then router 1 needs to have support for CHAP for it to be authenticated by router 2 using CHAP. If router 1 is using PAP to authenticate router 2, then router 2 needs support for PAP. It needs to be able to support PAP for it to be authenticated by that. Otherwise, different authenticators can use whatever they want as the authentication protocol. LCP also uses the magic number. I've talked about the magic number. It uses that to detect link loops and other expectations. A magic number is a random number, and the random mechanism must ensure that the probability of generating the same magic number at both ends is close to 0. So this is the LCP packet format, and those are the meanings of the different values. The code field can contain 1, can contain 2, or 3, or 4. Now 1 is for a configure request, which is a configuration request packet, and 2 is a configure ACK, which is a configuration success packet, which the authenticator sends to the other end, or the one device sends to the other device, telling it the configure has been a success. The configure non-acknowledged is configuration parameter need to be negotiated, and the configure reject is a way of saying, I cannot identify what you're saying. So what are we trying to say? When we send link control packets, when we are negotiating the link control protocol negotiation, the first phase, we are going to use link control protocol packets to negotiate it. And these are the types of packets we are going to be sending. If it is a normal negotiation, we are going to use only the configure request and the configure acknowledgement. If it is an abnormal negotiation, we are normally going to have configure request and one of these depending on what the abnormality is. Let us first discuss the normal negotiation. In a normal negotiation, we exchange just the configure request and the configure acknowledge. In our example, R1 and R2 are connected through a serial link, and they are running the point-to-point protocol. After the physical link becomes available, R1 and R2 are going to use link control protocol to negotiate link parameters. Now, in our example on this slide, R1 sends a configure request packet, as you can see. This packet carries the link layer parameters that have been configured on R1. For example, it says, oh, my maximum receivable unit is 1,500. The authentication type I've been configured with is password authentication protocol, and my magic number is A. So these parameters are going to be sent in this configure request packet all the way to router 2. And router 2 can identify and accept all the parameters in the packet. It identifies and accepts all the parameters in the packet. If it does, it's going to send a configure acknowledgement. I acknowledge everything you're saying is what I believe to be true, and so I acknowledge your request. Now, router 2 will also send its own configure request with its own interface parameters. Maximum receivable unit is 1,500. Password authentication protocol is the one used for authentication, and the magic number is B. It's going to send those in its own configure request. And if router 1 accepts, acknowledges, and accepts all the parameters, it's also going to send its own configure acknowledgement to the other end. Now, what happens if router 1 does not receive this configure acknowledgement packet? It's going to retransmit the configure request packet every after 3 seconds. As long as it's not receiving the configure acknowledge packet, it's going to keep sending a configure request packet every after 3 seconds. However, if router 1 does not receive any configure acknowledgement packet after sending this 10 times consecutively, it's going to consider the peer end unavailable, and so it will stop sending the configure request. This is for normal negotiation. But I just talked about abnormal negotiation. Now, there are two ways abnormal negotiation can happen. Excuse me. First of all, there might be a parameter mismatch. Look at this example. Router 1 here thinks the maximum receivable unit is 2,000, whereas router 2 thinks it is 1,500. The parameters are the same. Router 2 acknowledges the parameters on router 1, but there is a parameter mismatch. They don't match. The values they know are different. This guy says, oh, we're supposed to be exchanging 2,000. This guy says, no, it's 1,500. There is a disagreement. Now, what happens in a case like that? If router 2 receives a configure request from router 1, and router 2 can identify all the link layer parameters. It knows about the maximum receivable unit. It knows the authentication type. It knows what it means. It knows what magic number means. But it does not agree with the values in the parameters. The parameter value negotiation fails. Not the parameter itself, but its value negotiation fails. In that case, R2 is going to send a configure non-acknowledged, configure NAC, to R1. The configure NAC packet is going to contain only the acceptable link layer parameters. It's going to send the link layer parameters it knows and it accepts. It's going to send those to router 2 and after router 1, and after router 1 receives that, it's going to modify its values. It's going to modify its values to match the ones it's been told in the configure NAC packet. So it will reselect other locally configured parameters according to the link layer parameters in the packet and resends the configure request that way. So in this case, the parameters would be matching and then we'll receive a configure acknowledgement. Of course, after that, we'll also send our own configure request for which we shall receive a configure acknowledgement. That's the first abnormality, parameter mismatch. But there is also a case where router 1 is going to send a parameter that router 2 completely knows nothing about. Look at this example. Router 2 knows about the maximum receivable unit, the value is 1,500. The authentication type, the value is PAP. The magic number, the value is B. The magic number value is A, authentication type is PAP, maximum receivable unit is 1,000. They are all the same. However, look at router 1. Router 1 knows of another parameter XXX, which has a value XXX. Router 2 knows nothing about this parameter. It does not recognize this parameter. This is the second abnormality. So after receiving a configure request from router 1, router 2 returns a configure reject packet to router 1 if it cannot identify some or all of the link layer parameters carried in the packet. The configure reject packet contains the parameters that router 2 cannot identify. So when it sends that, it says, no, you know what? I don't identify that. I've only been told about this and this and this. I don't know what this is. I don't even want to see it. So after receiving the configure request packet, reject packet, router 1 will resend a configure request packet to router 2. That will contain only the parameters that router 2 can recognize or identify. Of course, on receiving that configure request, this guy will send his configure acknowledgement, send his own configure request, and get a configure acknowledgement back. This is going to be the negotiation. And as I've mentioned, in LCP negotiation, we are going to negotiate a number of things, and among them is the authentication type. Now, if the authentication type has been configured, if authentication on this link has been configured, it's either going to be password authentication protocol or challenge handshake authentication protocol. Why not talk a bit about password authentication protocol? This is one of the authentication modes supported by point-to-point protocol. So after LCP negotiation is complete, the authenticator requires the peer to use password authentication protocol in this example. So password authentication protocol is a two-way authentication protocol and uses just two packets. It's a two-way handshake authentication protocol. The password, however, is transmitted in clear text on the link. In security, do not advise to use that. So what exactly is going to happen? The peer is going to send an authenticate request. Inside this authenticate request packet, there is going to be the username, and his password. Meanwhile, on the authenticator, we will have configured a username and password of those that are allowed to log into. So when the peer sends the authenticate request, it will contain his own username and password. The authenticator will then check the local database of usernames and passwords to see whether there is a match. If there is a match, the authenticator will send an authenticate acknowledgement. Now, it is important to note that this method, this authentication, is two-way. My representation right here shows just router 1 authenticating router 2. But clearly router 1 will also need to speak back, and it will need router 2 to authenticate it. And so there will be a case where this guy is an authenticator and this guy is a peer. It is two-way. It is very important. For the communication to take place, it is going to be two-way authentication. Of course, router 2 may decide not to authenticate. Maybe it uses non-authentication, but both of them can authenticate the other. In other words, if they match, the authenticator will return an authenticate acknowledge packet indicating that authentication is successful. And if they don't match, the authenticator will return an authenticate NAC packet indicating that authentication is unsuccessful. That is for password authentication protocol. Again, I've mentioned the authentication messages are sent in plain text, in clear text, meaning if someone taps right here and uses the packet sniffer and captures packets, they are able to see your username and password exactly the way you typed them. It is not secure. A better authentication protocol that PPP supports is challenge handshake authentication protocol. Now, when we use challenge handshake authentication protocol, after our link control protocol negotiation is complete, if we are using challenge handshake authentication protocol, it means the authenticator will require this peer here to use CHAP for authentication. Now, CHAP, unlike PAP, uses 3 packet exchanges. And the process is simple, as illustrated here. First of all, the authenticator is the one that initiates the authentication for CHAP. We have seen for PAP, the peer is the one that initiates the authentication, says, hey, this is my username and password, please give me access. Say, oh yeah, I have that username and password, go ahead and use resources. Now in CHAP, it is the authenticator that starts the authentication process. And what he does is begin by sending a challenge to the peer, to the one who wants to be authenticated. The challenge packet basically contains a random number and the ID. Now, when the peer receives this challenge packet, the peer will perform an encryption calculation in MD5. It's going to create a hash. It's going to get the ID, combine it with the random number and its password, and generate an MD5 result. It is this result that it sends with its username. Notice that inside the generation of this result, there was the password. Now it sends its username and the MD5 result plus the ID. This is the response, and its code is 2. The code of the challenge is 1. Now, when this guy, the authenticator, receives this response, it has the MD5. And it has the username. However, it also has the database of usernames and passwords. What is it going to do? It's going to get hold of this username and search for its password in the database. After getting that, it's going to get hold of its random number that it sent, and also the ID that it sent, and use them by itself. It gets the password in its database and the random number it sent, and the ID it sent, uses them by itself to create an MD5 result, its own MD5 result. After getting its own MD5 result, compares it with the MD5 result that came from the peer, and if they match, then authentication succeeds. If they don't match, authentication does not succeed. Again, when the authenticator receives the response packet, the authenticator will locally search for the password that corresponds to the username in the response packet. And after obtaining the password, the authenticator encrypts the password using the same formula as the one used by the peer. Then the authenticator compares the digest obtained through encryption with that in the response packet. If the digests are the same, the authentication succeeds, and if they are different, the authentication fails. What's the beauty of this? Let us say some evil actor tapped this cable right here and started using a packet sniffer like Wireshark to capture packets. Instead of seeing the password, they are going to see an MD5 result. And guess what? They do not know the other values that can be used to calculate and generate the password that this guy is accepting. So we make life harder for the attacker to be able to get what we are trying to communicate. So in CHAP authentication, the password of the peer is encrypted before being transmitted, which greatly improves security. However, you should note that in this example, I have talked about MD5. MD5, which is a digital signature scenario and password encryption, it is an algorithm that has security risks. In actual scenarios, I would advise you to use more secure encryption algorithms. Advanced Encryption Standard, RSA. And when you use RSA, be sure to use 2048 bits and above. You can also use SHA-2 or HMAC, SHA-2, and other more stronger algorithms. Now, of course, after authentication negotiation, we say it first stage is LCP negotiation. Second stage is authentication negotiation. And in authentication negotiation, we are either going to use PAP, which I've discussed, or we are going to use CHAP, which I've discussed. After step 2, we go to step 3, which is network control protocol negotiation. Let us look at it. Now, network control protocol negotiation for IPCP, IP control protocol negotiation, provides us 2 negotiation modes. So, but basically, NCP negotiation is used to establish and configure different network layer protocols and to negotiate the format and type of data packets transmitted on the data link. In our example, we are going to use IPCP to discuss because it's one that is commonly used on networks today. So we have the static IP address negotiation, and we also have the dynamic IP address negotiation. This illustration right here is for the static IP address negotiation. Static IP address negotiation means this guy here has his static IP configured, this guy here has his static IP configured. So what is going to happen? The first packet from router 1 to router 2 is going to be a configure request specifying his own interface IP. Now, each end basically will send a configure request packet carrying the locally configured IP address. And the point is, after receiving the packet from the peer end, the local end will check the IP address in the packet, and if the IP address is a valid IP, number 1, is it a valid IP? Number 2, does it conflict with mine? Those are the 2 questions that are asked, and it's very important to know they are the only questions that are asked. If the IP address is a valid unicast IP address, and is different from my locally configured IP address, there is no IP address conflict, then the local end considers that the peer end can use this IP, and so it responds with a configure acknowledge packet. Those are the 2 things the peer end checks. 1, is the IP you send a valid IP? Is it a valid IP? 2, is it not the IP on my interface? Well, if both answers are yes, it will consider that the IP can be used by the peer, and so will send a configure acknowledgement. Now, I say this is two-way. The peer, in this case R2, will also send its own configure request with its own interface IP, and this guy will check if the IP is valid, unicast. It's a unicast IP, it's not broadcast, it's not multicast. If it's a unicast IP and it's not his own interface IP address, he will send a configure acknowledgement. That is NCP negotiation in static negotiation. But NCP, particularly IPCP, also supports dynamic IP address negotiation. So in dynamic IP address negotiation, we have 2 devices connected to each other, in this case via serial link, running point-to-point protocol, but one of the interfaces does not have an IP address. The other interface has an IP address. So what NCP dynamic IP negotiation is going to do in this case, this router that is having an IP address is going to allocate his peer an IP address so that they can communicate. They are not selfish, right? Let us walk through this example. In this example, router 1 node says that they're using PPP and the link is up, but he has no IP address. So he sends a configure request packet saying, hey, I have no IP address by the way, but we really need to talk. So this 0.0.0.0 address is what R1 uses to request R2 to assign it an IP address. Now when R2 sees that, it's going to send a configure non-acknowledge. We talked about that, non-acknowledge, and it's telling it, you know what, you can use this IP. It's good and I can communicate with it. So you will send a configure non-acknowledged configure NAC to R1, giving it an IP option that it can use. Now R1 will resend the configure request, but now with the IP that it has been assigned by its peer, for which the peer of course will send a configure acknowledge and also send its own configure request with its own interface IP, and it will receive, or R1 will send its configure acknowledgement for that IP. So we see in this example that a device in PPP protocol can assign its peer an IP in dynamic IP address negotiation. So let me walk through very briefly configuration of basic PPP functions. First of all is setting the link protocol to PPP. Just get into the interface view and use the command link protocol PPP. Now remember, if you're connected using serial interface, the default is going to be PPP, so you wouldn't need that command. And then you would go and configure a timeout period. This is the time with which the local end will wait before receiving a reply packet from the peer end. Within that specified negotiation timeout period, the local end will be resending. The default is 3 seconds. I talked about that. So the PPP timer negotiate seconds, you specify the number of seconds. So if your authentication you're going to use is PAP authentication, you would need to create a local database of usernames and password. You do that in the AAA view. So you create a local user, specify the username, and then you do the password, specify the password. And then you specify the service that that user can use, in this case PPP. Then you'll go to the interface and say the PPP authentication for anyone who accesses you in PPP, using point-to-point protocol, use password authentication protocol authentication mode. So you'll go to the peer that will need to be authenticated and say, your PPP PAP local username is that username. This is now going to be the same username you told that guy to store in his database, and the password is this password, which will again be the password you told that guy to store in his database. Now, if you're using challenge handshake authentication protocol, you will still need to create a database of usernames and passwords. So you say you have a local user in AAA view, have a local user, specified the username, and go ahead and specify the password, and that local user is allowed to use PPP service. Now, you'll go to the interface view and say the PPP authentication mode is CHAP, this time not PAP. Now, when you do that, you'll go to the interface view of the peer device and say your PPP CHAP username is that username, and the PPP CHAP password is that password. Once you do that, there's going to be communication. This is a simple configuration example. You can see we have R1 as the authenticator and R2 as the peer, and R1 has 10.1.1.1/30, R2 has 10.1.1.2/30, and the requirement is to enable PAP authentication on the PPP link between R1 and R2, configure R1 as the authenticator and configure R2 as the peer. Now R1, the authenticator, is the one that needs to have the database of usernames and passwords. So we shall get to the AAA view of the authenticator and then create a user called Huawei in our example, and the password is Huawei123. Then we shall say the user Huawei should have access to the service PPP, right? Then we shall get to the interface view again of the authenticator, the interface view of the authenticator, and say the link protocol is going to be PPP. Now, this is a serial link, so even if we don't run this command, it will be there by default, but we would need to run the PPP authentication mode is going to be password authentication protocol. And then, of course, we shall assign the interface and IP address. Now, on the peer that will need authentication, the only thing we need to do is to assign an IP address and then set the authentication, the link protocol, which is PPP. And again, this is a serial link, by default it will be TPP. And then we would need at the interface to say, hey, your PPP password authentication protocol local username is Huawei, and your password is Huawei123. So when this guy sends a packet, it will have his local username and his password. And this guy will check that in his database of usernames and passwords and find a match and allow them access. My next example is an example configuring CHAP authentication for a PPP link. Again, we have R1 and R2, but in this case, the authenticator using PPP expects the peer to be authenticated using the CHAP authentication CHAP authentication. So we are configuring again R1 as the authenticator, meaning is the one that needs the database of usernames and passwords on him. R2 needs his username and password configured on the interface so that he can tag that on a packet when he wants to send it to R1. So again, we shall go to the AAA view and create a username, in this case called Huawei, give him a password called Huawei123. Go ahead and give that user, Huawei, access to the service PPP. We shall then go to the interface, serial 1/0/0, set the link protocol to PPP again. This is a serial link, and so PPP will be the default. You will actually find this command there for you if it is a PPP, if it's a serial link. But you will need to set the PPP authentication mode to CHAP. So the configurations of R2 is simply getting to the interface view. This again can be configured, can be ignored. It's there by default on serial links. And then you set the PPP CHAP username to Huawei, PPP CHAP password to Huawei123. So that when router 1 attempts to access router 2 attempts to access router 1, he will ask for the username and password, and those are already right there on the packet, and so he'll get authenticated. Ladies and gentlemen, that brings us to the end of PPP protocol. In the next video, I'll be covering point-to-point protocol over Ethernet, a case where we encapsulate our point-to-point protocol packets, the ones we've been talking about all through this video, we encapsulate inside an Ethernet frame. That will be in the next video. I hope this has been informative for you, and thank you for viewing.